Welcome to this lecture of graph theory. In this lecture, we shall study the proof of Tutte's one-factor theorem. Before taking the statement or the proof of the Tutte's one-factor theorem, we shall recall some definitions that we require during the proof. The first definition is a matching M in a graph G is called a perfect matching if M saturates all the vertices of G. And here we note that a perfect matching is also known as a one-factor. Now here in this definition we have used a term saturating a vertex, and a matching M of a graph G is said to saturate a vertex V in the vertex set of G if there is an edge in M incident on V. So we have a matching M in a graph G is a perfect matching if it saturates all the vertices of G. That means if this matching contains all the vertices of G. Now here is one more definition that we require in the proof. A component of a graph G is called an even component or an odd component accordingly if it has an odd number of vertices or an even number of vertices. And the notation for denoting the number of odd components in a graph is K naught of G. So this K naught of G denotes the number of odd components in a graph G. Now let's come to the statement of Tutte's one-factor theorem or Tutte's perfect matching theorem. Or this is the theorem that tells us what should be the conditions on a graph so that there is a perfect matching in that graph. Now Tutt states that a graph G has a one factor if and only if the number of odd components in G minus S is always less or equal to the number of vertices in S for all subsets S of V of G. So therefore what we have, first of all we have a graph G, and suppose it has the vertex set V and suppose the edge set E. Now from this vertex set we will have to choose the subset S. So S is the subset of the vertex set of V. Now if this graph G has a property that when we remove the set S from V of G, then G will be broken into some components, then the number of odd components in G minus S must be less or equal to the number of vertices in the chosen subset S. If this thing happens for every subset S contained in V of G, then the graph G will necessarily have a perfect matching or a one factor. So now let's take up the proof of this theorem. First of all, we assume that a graph G has a one factor. So let G be a graph having a one factor. That means having a perfect matching. We show that this number of odd components in G minus S, this is less or equal to order of S for all subsets S contained in vertex set of G. So now let this O1, O2, so on, OK be the odd components in G minus S. Let these be the odd components of G minus S for some S contained in vertex set of G. We shall show that this K is an odd number here. Now let's first construct the figure for understanding this proof properly. So we have the odd component. Suppose this is one odd component here. So this is suppose O1, and here we have another odd component. Let's name this as O2, and so on. Let this be an odd component. Let's call this as OK. And now here we have a graph remaining the set of vertices of G, which is the vertex set S. And suppose this is the whole graph. Okay, so suppose this is a graph and these are O1, O2, OK, they are the odd components in G minus S, so this is the whole graph G, and S is a subset chosen from the vertex set of G. Now since we are assuming that the graph G has a one factor, that means there is a perfect matching in this graph. So that means there is a set of independent edges in this graph that saturate all the vertices of G. So that set of independent edges, that perfect matching, will saturate in fact all the vertices of these odd components. Now the first thing that we shall note here is that if we have some vertex here in the first odd component, that's O1, and a vertex, some vertex in the second odd component, suppose O2, then this vertex in this odd component, suppose V, this cannot be adjacent with any vertex in O2, this cannot be adjacent with any vertex in OK, because these are disconnected components of G. And the second thing that we note here is that this vertex from any OI will be adjacent to some vertex within the same OI, or it can be adjacent with some vertex of S. So therefore the only possible adjacencies for any odd component will be either the vertices are adjacent within that OI, or that vertex is adjacent with some vertex of S like this. So these are the only possible adjacencies for OIs. Now, since the graph has a perfect matching, and if we suppose take up this O1, it has now odd number of vertices. Therefore, at least one vertex of this O1 must be adjacent with some vertex of S for the existence of a perfect matching. The main reason for this existence of such a vertex is that a graph with odd number of vertices cannot have a perfect matching. So therefore, if we take this O1, it has odd number of vertices because it is an odd component. So therefore, it cannot contain a perfect matching. So for the existence of a matching which saturates all the vertices of O1, there must be at least one vertex in O1 which is adjacent outside of O1. But outside of O1 here means it cannot be adjacent with any O2 or up to OK. It has to be adjacent with some vertex of S, because S was a set whose removal from G induced this odd component O1 here. So therefore at least one vertex from every OI must be adjacent with some vertex of S because of the existence of a perfect matching. So we shall recall these things here. Now for each I, the vertices in OI can be adjacent within OI or adjacent to some vertex of S, and at least one vertex of every OI must be adjacent to a distinct vertex of S. Now this vertex is distinct because of this reason. Suppose if we have a vertex V from O1 and a vertex suppose U from O2, if they are adjacent with the same vertex in S, then since there is a perfect matching in the graph, and if it contains suppose these two edges, then that matching will not remain a matching at all. So therefore for every vertex we must have a different vertex in S which is adjacent with some vertex of OI, or for at least one vertex in every OI there will be a different vertex in S such that the vertex of that OI is adjacent with that vertex of S. So therefore there is at least one vertex in O2, let's call that U, it will be adjacent with some different vertex of S, and similarly there will be some vertex, suppose let's call that as VK, it will be adjacent with some different vertex of S here. So this obviously means that for every OI there is at least one different vertex in S such that there is an adjacency of this form. So this clearly implies, so this means S has at least k vertices. That is, this k is less or equal to order of S, which actually means this number of odd components in G minus S, this is less or equal to order of S. So this is the necessary part of the proof, that if there is a perfect matching in a graph, then the number of odd components in G minus S must be less or equal to the number of vertices in S. Now let's take up the converse part. So now conversely, assume that the number of odd components in G minus S, this is less or equal to order of S for every S contained in vertex set of G. We shall show that G has a perfect matching. Now assume to the contrary that G has no perfect matching. Assume to the contrary that G has no perfect matching. or a one factor. So we have the graph G and we are assuming it has K naught of G minus S less or equal order of S, and suppose G has no perfect matching. Now join the non-adjacent vertices of G, join the non-adjacent vertices of G until we obtain a graph, say G star, such that this is G star plus UV has a perfect matching for any non-adjacent pair of vertices U and V. So what we are doing here, now since the graph G has no perfect matching, now we will keep on adding the non-adjacent edges in G until we obtain a graph G star such that for any non-adjacent pair of vertices UV in G star, if we add the edge between UV, then G star plus UV will have a perfect matching. So this means that G star is a maximal graph such that G star does not have a perfect matching, but adding any edge in G star, we will get a perfect matching in G star plus that added edge. So this construction makes it obvious for the now moreover now since we are adding the edges in G to obtain the graph G star, which is a maximal graph having no perfect matching. Now if we add that edge between any two odd components of G minus S, then those two odd components will merge together to create an even component, because both of those two odd components will have odd number of vertices. So if we connect an edge between them, then they will create a single connected component, and that will have odd plus odd even number of vertices. So that means joining or adding edges in G to obtain G star, the number of odd components cannot increase. So moreover, adding edge between any two odd components will create an even component. Therefore, this K naught of G star minus S will always be less or equal to the number of odd components in G minus S. Now this is itself less or equal to order of S. So that means the condition K naught of G star minus S less or equal to order of S must also hold for this maximal graph G star as well. So now we shall work on the graph G star and try to obtain a contradiction, because we have assumed the existence of no perfect matching, because we have assumed to the contrary that there is no perfect matching in the graph. Now first of all, we shall show that the graph G or the graph G star has even number of vertices, and in fact it is an obvious thing that the existence of perfect matching forces the graph to have only even number of vertices. A graph with odd number of vertices can never have a perfect matching, because every edge saturates two vertices at a time. So now if this S is equal to phi, then order of S is equal to 0, and we have number of odd components in G star minus S. This is less or equal to order of S, so this is equal to 0. So this means that this G star minus S, while S is equal to phi, has no odd component. But here in this case, so this means G star has no odd component. But now G star is a connected graph, so and G star has no odd component. That means G star itself is not an odd component. It means that G star is an even component. So this means G star has even number of vertices. So this implies G star itself is an even component. That is the number of vertices in V of G star. This is an even number. This is equal to even, and suppose it has now n number of vertices, where n. Now let's pick up a vertex. So now let K be a set of vertices of G star whose degree is n minus 1. So we can write it in this way also, that is this K is equal to vertices V belonging to vertex set of G star such that degree of V is equal to k minus 1. Not actually k minus 1, it's n minus 1. Sorry, it is n minus 1. So we are taking a vertex set from G star k, and every vertex in k has degree exactly equal to n minus 1. Now noting that the graph G star is assumed to have n number of vertices where in fact n is even, then a vertex of degree n minus 1 means this vertex must be adjacent with all the remaining vertices of G. So now consider the graph G minus k. Now at this stage we first note that this k is now not equal to V, because if k is equal to V, then every vertex in G star has degree n minus 1, that is G star is a complete graph of order n, where this n is an even integer. But we know that a complete graph having even order must have a perfect matching, so this means G star has a perfect matching. But as per our construction of G star, we had constructed G star in such a way that G star does not have a perfect matching, and then G star plus n edge has a perfect matching, which is a contradiction to the construction of G star, which is a contradiction because G star is assumed to have no perfect matching. Now consider the graph G star minus k. Consider the graph G star minus k. Then we claim every component of G star minus k, every component of G star minus k is complete. So we are here assuming that every component of G star minus k is complete, that is a complete graph. So assume to the contrary that there is a component in G star minus k, there is suppose component to G1 in G star minus k, which is not complete. Then in G1 there are vertices x, y, z, say x, y, z, such that x and y are adjacent, y and z are adjacent, but x and z, they are not adjacent. So we are assuming a situation of this form. So we have a vertex y here, it's adjacent with a vertex x, it's also adjacent with a vertex z, but this x and z, they are not adjacent with each other in the graph G1, which is a component of G star minus k. Then obviously this degree of y in G star, degree of y is equal to, it is in fact less than n minus 1 in G star. Now, why the degree of y is less than n minus 1 in G star? We have first constructed a vertex set k from V of G, and every vertex in K has degree equal to n minus 1. Now we have removed all the vertices from K, that means from G star we have removed all the vertices whose degree is equal to n minus 1 and obtained a graph G star minus K. And we have chosen this component G1 from G star minus K. So obviously now this G star minus K, this will not contain any vertex of degree equal to n minus 1. So therefore now y is a vertex from G star minus k, because it's a vertex of G1, therefore this degree of y must be less than n minus 1. And in fact the degree of x, which is from G1, also must be less than n minus 1, and degree of z should also be less than n minus 1. Now since this y is adjacent with x and y is adjacent with z and degree of y is less than n minus 1, so there must exist a vertex, say w, like here. There must exist a vertex w such that y and w are not adjacent with each other. So therefore we will have a situation like this, a vertex existence of a vertex w in G1 such that y and w are not adjacent to each other. Thus there exists a vertex w belonging to V of G1 such that this y, this is not adjacent with w. Now by the choice of G star, now by choice of G star, here we mean we have constructed the graph G star as a maximal graph such that adding just one more edge in G star we get a graph that has a perfect matching. So this G star now does not have a perfect matching, but G star plus any edge will have a perfect matching. We have this G star, suppose if we add the edge xz and also the graph G star plus the edge YW have perfect matchings. Say M1 and M2. So we have a perfect matching in G star plus xz, and this perfect matching must contain the edge xz also, because it is only this xz that has made it possible for G star plus xz to have a perfect matching. Now similarly in G star there is no perfect matching, but G star plus YW has a perfect matching. So therefore this perfect matching must contain the edge YW also. So clearly this edge xz belongs to the matching M1, and the edge YW, this belongs to the matching M2. So for the matching in G star plus xz, we have named that perfect matching as M1, and the matching G star plus YW, we have named that matching as M2. This M1 must contain xz and M2 must contain YW. Now let H be a graph induced by the edges of M1 and M2. In fact, we are constructing the graph H to be the graph induced by those edges of M1 and M2 which are not both in M1 and M2. So we construct a new graph H which is induced by those edges of M1 and M2 which are not both in M1 as well as in M2. So therefore the graph H is induced by the edges of M1 but not in M2 and the edges of M2 but not in M1. So that means this H contains the edges of M1 symmetric difference M2. Now obviously the components of H are even cycles. The components of H must be even cycles, since the edges alternate between edges of M1 and M2. Now two cases arise here. Now two cases are in this way, that when we are constructing the graph H whose edges belong to M1 or M2 but not both, then these two edges x, z and yw, they can be in the same component of H or they may be in a different component of H. So now the first case is the edges xz and yw belong to different components of H. Now let's pick up a cycle C. Let yw be on a cycle C of H, and this C does not contain the edge xz. So we have a situation of this form. So therefore we have this YW is an edge which is on a cycle C, and in fact this will be an even cycle. So now let's have, like, this is another edge from the matching like M2, and this is also an edge of M2 in the cycle C. So suppose this is a cycle C, and now let us draw the alternating edges. So this is an edge of M1 on this cycle, and this is the edge of M2 on this cycle. And similarly now we have another cycle in the graph H that contains the edge xz. So because we are assuming that this xz and yw, they are on two different components of H, So this is the cycle which is the edge xz, and this is from the matching M1, and it will similarly have some other edge here which is from the same matching M1, and then since the edges alternate between M1 and M2, so therefore there may be the edges of this 4. We are creating the C4s here, the cycle is of length 4 only, but the general thing is that the cycle C and every cycle in H will be a cycle of even length. So some cycle may have length 4, some may have length 6 and 8 and so on. But for an example here, we are just construct the cycles of length 4 only. And now in the original graph, we have these two edges also. But these two edges, the edge yx and yz, they are not the edges in C. Sorry, they are not the edges in H, because H is constructed from the edges of M1 and M2, and the matching M1 contains xz, so it cannot contain xy or zy, and similarly the matching M2 contains yw, so again M2 cannot contain the edges yx and yz, so therefore this yx and yz, they are not the edges of the graph H. Now if we look into this graph and we can construct a matching here now, so then edges of M1 in C, then edges of the matching M1 in C. So that means this edge. So this is here actually M1. Now the edges of M1 in C and those edges of M2 that do not belong to C, give a perfect matching in G star. So now what we are writing here, now in this situation when we have a cycle C, it contains the edge yw but does not contain the edge xz, then from this construction we can construct a matching by picking up those edges of M1. So that means we have to pick up this, suppose the red edge here, and those edges of M2. So this is an edge of M2 here, the black edges, and we will pick up those edges of the M2 which do not belong to the cycle C. So in order to construct this matching here, we will pick up all the M1 edges of C and all the M2 edges of the remaining edge. So that means except this edge and this edge from M2. So picking up all the red edges from this part C, and then delete these two edges M2 and M2 from C and take up all the M2 edges from the remaining graph H will give us a perfect matching in G star. Now we can see here this the way we have constructed this matching by taking these M1 edges from C. It does not contain the edge YW because this is not an edge of G star. And similarly in this construction we have taken the edges of M2 from the remaining graph H, so it obviously does not contain this edge and it does not contain this edge, and xz was not an edge of G star, so we are not taking xz into consideration for the construction of matching now. So in this situation we are able to construct a matching in G star without the edges xz and yw. So which is a contradiction to the fact that G star does not have a perfect matching. So which is a contradiction. So this was the case when this yw and xz are not in the same components. Now the second case is if xz and yw belong to the same cycle in H. So now let's try to construct a kind of a situation here. So we have the edge suppose yw here, so this is the edge yw, and then we have the edge suppose xz here, so this is the edge xz. Now these both edges belong to the same cycle in H. So now let's construct some more edges here. So since the edges alternate between M1 and M2, so now suppose the next edge is this, and suppose the next edge is like this here, and similarly here and here. And now let's try to construct some more edges which is suppose like this and this. So now these black edges, so we shall try to construct the edges of M1 and M2 differently. Suppose this is YW and suppose this is the edge XZ. Now here we will have the next edge from the matching M1, and similarly here we will have an edge from the matching M1, and here we will have a matching edge from the matching M2, and suppose also an edge from the matching M2, and so on like this. So now let's connect this edge here, and let's connect this edge here. So we can have this kind of a situation here, a cycle that contains both the edges YW and XZ. Now we are using these as M1 edges and the black colored edges as M2 edges. And in the original graph, we will have the adjacencies like this, Y, X, and YZ. So these are the adjacencies in the original graph, but these two edges are not the edges of H. Now let's assume without loss of generality that this Y, W, and X, Z are in the same order in the original graph G star. Then what we do, so let's first write down these details here. Now this is the case number 2. So then the edges of, then in this case, the edges of M1 in belonging to this sequence like this Y, W, so on up to Z. So that means the edges that are on this part. So it is like this. The edges of M1 that belong to this part, that means these red edges on this part, and together with the edge, this YZ, and the edges of M2 and the edges of M2 not in the same path YW, so on up to Z, constitute a perfect matching in G star. So now what we are doing here, we have now a second case where this YW and XZ belong to the same component, say C, same cycle C. Then we start with this, we take those edges of M1 which belong to this part, Y, W, and so on in this way up to this Z. We take all the red edges from Y to Z, Y, W, so on up to Z. That means we are taking this edge and this edge. Then we also take the edge YZ here. That means this edge, because this is also an edge of the original graph. Then together with those edges of M2 which are not here in this part. So that means we are deleting this edge, we are not taking this edge, we are not taking this edge, and we are taking all the remaining edges of M2. Then this will give us a perfect matching in G star. Now in fact, in the construction of this perfect matching, we have not taken the edge YW into consideration, and obviously this was not an edge of G star, and we have also not taken the edge XZ in consideration, and again this was not an edge of G star. So we have taken only those edges of this path YW, so on up to Z, which are from M1, and then we have also taken the edge YZ, this is also an edge in G star, and then we have taken the black edges in the remaining part of the graph here from H, and this constitutes a perfect matching in G star, which is again a contradiction. So thus we have obtained a contradiction in both the cases, that whether these two edges YW and XZ belong to different components or the same components, then we get a matching in G star. So this contradiction was the consequence of the fact that we had assumed that the components, there is some component in G star minus K which is not complete. So that means this assumption here, that we have assumed that there is a component in G1 which is not complete, it is not true. So therefore this statement is not true. So hence every component in G star minus K is complete. So hence every component of G star minus K is complete. Now we also have, and we have finally this K naught of G star minus K. This is obviously less or equal to the number of vertices in K, because this was the given condition and this is our assumption hypothesis, that for every subset K contained in vertex set of G, we have the number of odd components in G star minus S is less or equal to order of S. So therefore this statement must also be true for this K, which is also a subset of the vertex set of G. So now we have the situation of this form. Now we shall construct one graph here that will help us in writing the remaining details of the proof. So first of all, we have suppose some odd components here. So suppose this is an odd component here, and this is suppose the odd component, let's call it G1, and suppose then there is another odd component, let's call it G2, and so on. Then there is another odd component, let's call it Gk. And suppose now we have some even components also here, so let's call it E1 and so on. And suppose let's have an even component, suppose EL here. And this is now here is the graph, which is the set of vertices K. So we are taking, this is the vertex set K, this is the whole graph G, this is the vertex set K here, and this is the set of vertices where every vertex in this K has degree n minus 1, and these are the odd components here, so they have always odd number of vertices, and similarly here, and these are the graphs that have even number of vertices. Now as per our construction till now, we have the number of odd components is less or equal to the number of vertices in this K. So therefore this K is less or equal to the number of vertices in this rectangular region K. And second thing is that these all components G1, G2, Gk or E1, E2, EL, they are all the complete subgraphs. They are all the complete components of G minus K. Now when we are removing K from the whole graph G, and this G1, G2, Gk, they become the odd components, or they become the distinct components of G star minus K. That means for every Gi, there must be a vertex in Gi that's adjacent with some vertex of K. Okay, so therefore we will have, since there are odd number of vertices here, so there must be a vertex which is adjacent here. And similarly from the second odd component, there must be a vertex in G2 that's adjacent here, and so on, and this thing will happen for all the odd components. So we will have these kinds of adjacencies from Gi's into K. At least one vertex of Gi must be adjacent with some vertex of K. And this is also made possible by the fact that the number of odd components here, it is less or equal to the number of vertices in the whole of K. So therefore, for every odd component, there will be a different vertex in K such that there is an adjacency from some vertex of Gi into the vertex of K. Now we will try to construct a perfect matching in this way. Now we have this E1. It is an odd, it's an even ordered complete subgraph of G minus K, G star minus K. Now since this E1 is a complete graph of even order, because we have already proved that all the components of G star minus K are complete, so therefore this E1 is a complete graph of even order, and we know that complete graph of even order always has a perfect matching. So therefore there will be a perfect matching like this. If it has just 4 vertices, then this is a perfect matching. If it has suppose 6 vertices, then this is a perfect matching, and so on. Similarly, this EL, they are all the even ordered complete graphs, so now they will have a perfect matching like this included within these complete even components. And now these GIs, G1, G2, Gk, they are the odd components of, but they are also complete, and there is at least one vertex incident or adjacent with some vertex of K. Now removing that one vertex, at least removing exactly one vertex from these GIs, the remaining graph will be a complete graph of even order. So therefore remaining we can construct a matching in this way. And similarly in G2, if one vertex is made adjacent with some vertex of K, then for the remaining vertices in G2, they will be the even number of vertices, and we can construct a perfect matching in this way for the remaining even number of vertices. And the same thing can be done in every odd component. One vertex connected with some vertex of K, and for the remaining vertices, there is a perfect matching because every even ordered complete graph has a perfect matching. So therefore in this way we have saturated all the vertices of even components. We have in fact also saturated all the vertices of odd components with the even number of vertices saturated within these odd components and exactly one vertex saturated by some vertex of K. Now the remaining vertices of K, they will also be saturated provided they have an even order. Now this K minus, now looking into this part K, in this part every vertex has a degree equal to n minus 1. So that means all these vertices, they are connected with all the remaining vertices of the graph. So if we take up any collection of this K, they will also induce a complete subgraph of the whole graph G star. So what we are trying to do here is that if the remaining set of vertices, like which is here, so this is the remaining set of vertices now in the graph G, which are yet to be saturated by a perfect matching. Now if we take a graph induced by these vertices only, and we take a subgraph induced by only these vertices, then that graph will also be a complete graph. If that complete graph has even order, then by the reason that we were just mentioning here for all these even components, these vertices will be saturated by a perfect matching within these vertices. And so we are only left to show that the remaining vertices that are yet to be saturated by a perfect matching in G star, these number of vertices must be even. And that obviously follows in this way. Suppose we have this is the whole graph G, and obviously we have already proved that the whole graph G has even number of vertices. Now if we remove any of these even components here, the remaining graph will have again even minus even number of vertices. So first of all, if we remove the component E1 which has even number of vertices, so we have removed this, then G minus this G star minus E1, it will have again even number of vertices. Similarly, removing all the even components minus so on minus EL also, the remaining graph will also have even number of vertices. Now the question comes to these odd components. Now if the number of these odd components is odd, then removing all these odd components together with the vertices that together with these vertices like this vertex and this vertex, then it will remove the even number of vertices from the graph, because all these odd components have odd number of vertices. Then we will add one more vertex to all of them, that will create the even number of vertices, and removing those even number of vertices from the whole of graph, we will be left with only this part of the graph. So this will have even number of vertices, and that will have then the perfect matching, because that will be a complete subgraph of G star. And second thing is, if all of these components are even in number, then simply removing these components here, the remaining K will all will have an odd order, and it will be a complete graph of order. Suppose some K, then it will also have a perfect matching, because it will have an even order and it will be an even ordered complete graph. So this is how we construct a perfect matching in the whole of G star. Now we write the same details here for better explanation. So we have therefore one vertex of each odd component is matched with a different vertex of K. This is because each vertex of K is adjacent to every vertex of G star. So we will match just one vertex from odd components to some vertices of K, and remaining vertices are matched among themselves. So here we mean that the remaining vertices of odd components are matched within the odd component, and the vertices of even components are matched within the even components, and the remaining vertices of K are matched within themselves. Since the total graph has odd even number of vertices, thus even number of vertices are matched. So thus even number of vertices are matched. And since the graph has even order, since order of vertex set of G star is equal to n is even, hence all vertices are matched. Or we can say hence all vertices are saturated. This implies there is a perfect matching. So this completes the proof of Tutt's one-factor theorem. Now let's again recall what we have exactly done. The main steps of the proof are, first of all, in the converse part, we construct a graph G star which is obtained by adding the edges to the original graph G to obtain G star, which is a maximal graph having no perfect matching. Then G star plus UV will have a perfect matching, and this perfect matching will obviously contain the edge UV. Then we pick up a vertex subset K from the vertex set of G star, and this K contains those vertices of G star that have degree equal to n minus 1. Then this K will not be equal to the whole vertex set of G star because G star is an even ordered graph and it does not have a perfect matching. So then we consider the graph G star minus K, and we claim that every component of G star minus K is a complete graph. For that thing, we assume to the contrary, that there is a component G1 which is not a complete graph in G star minus K. Then it gives contradictions in this way. We take a sequence of vertices x, y, and z such that xz is not adjacent. Then this degree of y is less than n minus 1 forces the existence of w, and yw is also not adjacent. Then we take a graph, then we construct a new graph H, which is induced by the edges of M1 and M2, where M1 is a matching, complete matching in, or the M1 is a perfect matching in G star plus XZ, and M2 is a perfect matching in G star plus YZ. Then H is induced by the edges of M1 and M2, which are either in M1 or in M2, but not in both of them. Then if the edges XZ and YW are in different components, then we construct a matching in G star by taking the edges of M1 from cycle C, which contains YW, and those edges of M2 which are not in the cycle C. Then this gives rise to a perfect matching in G star, which is a contradiction. And the next part is when these two edges XZ and YW belong to the same component, then we order the vertices in this way, X, W, Z, X, as we have done it in this graph. Then we take those edges of the cycle C which are on the sequence Y, W, so on up to Z, and then those edges of M2 which are not in this first part. It will again give rise to a perfect matching in G star, which is a contradiction. So this means that every component of G star minus K must be complete. Now since every component of G star minus K is complete, now we have some odd components here. For every odd component, we will connect one vertex with the vertex of K. So that will give the process or the existence or the validity that how the vertices are saturated, and all the remaining vertices are then saturated within themselves, that is within an odd component or within an even component or within the set of vertices which is K. So this gives rise to a perfect matching in the whole of G, and this completes the proof.